Good afternoon, everybody. Welcome to the ESRF webinar. Before announcing today's presentation, I just remind you that a few technical information. So this is brought to you via Zoom or on YouTube, and it will remain available on YouTube for replay. You are invited to use the question and answer box that is on the bottom of your Zoom window to ask questions for the speaker, and you are invited to upvote questions you feel should be answered in priority. I should also mention that this series of events is supported by the Streamline project of the European Commission. So to today's talk, today's speaker is Dan Mannix from the European Spallation Source in Lund and also affiliated with Institut Néel in Grenoble. Dan Mannix studied physics in Liverpool University, where he got his PhD in condensed matter physics in 1997. He then joined the ESRF as a postdoc on beamline ID20 and later as a beamline scientist on the XMUS CRG beamline. In 2007, he was hired as a CNRS scientist at Institut Néel in Grenoble. And 2014, he moved in secondment to Lund University. And since 2018, he is now at the European Spallation Source in Lund as a lead scientist of the Heimdall instrument. The talk of today's presentation by Dan will be New Attraction for Heat Harvesting Devices Exploiting Magnetism. Daniel, we are looking forward to your presentation. Thank you.
Okay, can you see my screen okay?
Yes, everything is fine.
Everything's fine, okay. So I'm going to talk about spin-caloritronic materials under this heading of a new attraction for heat harvesting devices exploiting magnetism. So this work really follows from a nice publication we got last year in Science Advances, where we basically could look inside these materials using Nanobeam in Nanobeam diffraction and image the domains inside these spin-caloritronic materials. So what I'm going to do here is go through a little bit those results again and highlight them again and put them in context with some new measurements that we've been making on these materials as well, using inelastic scattering to study the magrons in these materials too. So really I'll start off with an introduction for people not working in magnetism, why magnetism is interesting and how we use X-rays to probe magnetism. I will then move on to highlight some of these results that were in this paper using this nanodiffraction method that was developed basically by a combination of magnetic scattering and nanobeam on the ID1. Then I'll talk about revealing these magnetic excitations or magnons using inelastic scattering probes. And then finally, some conclusions and future perspectives. And one of the interesting perspectives of this is maybe in the future, how we can use this EBS light source. So we have some proposal accepted now, again, going back to ID1, where we want to try and use this new source and the exciting properties of this new source to continue studying these materials and hopefully move them very much further forward and build on these very nice results I'm going to show. So first of all, I'll say something about magnetism. Magnets are used extensively in technology in our society. They're used in medicine, for example, in MR imaging. They are markers in these imaging methods that we use for medical imaging. They're used in these green cars, these electric cars, the motors that drive green cars have magnets inside. They're also used to generate clean electricity inside these windmills, these wind farms. Another aspect of that can be these so-called kinetic batteries, where you actually store energy in the form of kinetical energy rather than chemical energy, and these can be accelerated or deaccelerated to take in electricity and store it and then give it out again, and that's seen these days as a viable technology. They're used in sound cancelling headphones, and what I really want to talk about here is the use of magnetism in electronics and communications industry, in Spintronics in particular. So I say something about Spintronics for those who don't really know. So way back in the 80s, where the digital age started, we started to use these kind of binary 0-1. This is the digital information that is stored, and these were used very small magnets as basically the zeros and ones. Way back in the 1980s, the thing that really developed in the 1990s that really exploded computing power was the discovery of the giant magnetic resistance effect. So here you can have a resistance that depends on the orientation of magnetic moments. So you can get a high resistive state or a low resistive state, and you can use that essentially to store this information. And that was really the start of Spintronics, really, the fact that you can have conductivity related to magnetic orientation. So there's a lot of research today that goes on in Spintronics, trying to look at how we can improve on these old technologies, whether we can actually get higher density storages by having much smaller domain size or much smaller magnets, packing them together. One idea there is using these skyrmions. These are very small topological magnetic states that arise in certain materials, and these can be just tens of nanometers across, so you could really pack an ultra high storage density if you could actually make a device, a storage device that actually exploit those skyrmion things. So at the moment there's a lot of intensive research in these kind of materials. Another aspect is domain walls and using domain walls in motion and studying domain walls and these kind of racetrack memories. So and another aspect of these materials, Spintronics, originally is using magnons or spin waves, and this is a field which is growing called magnonics, where you can actually use spin waves or magnons basically as information carriers in possible devices. And the advantage there is that using magnons or magnetic excitations uses a lot less energy than moving charges around. So this could be very low power consumption kind of electronics developments if you can use those kind of magnetic excitations rather than magnetic moments themselves or charge moments to move around. And of course, to understand these materials much better, we need really advanced probes. We need to develop much more advanced probes to study these on a nanoscale and how these things can evolve also in the time scale as well. So spin-caloritronics, what are these materials? These materials are about they have charge current, spin current, and heat current in one of the same material. And these currents can be interchangeable. So I put here as a sort of new spin on old physics, because the interchange of heat current to charge current has been well known since the 1800s. These are thermoelectric effects. So you can have the Seebeck effect, which is transformation of a heat current into electricity. or charge current. And the inverse of that is the Peltier effect. Where we go into spin-caloritronics is that we can actually use magnons to create a spin current and then transform that spin current to charge current using spin Hall effect and inverse spin Hall effect. So you can basically go around and get these interchange going via the spin current. And that can give a huge diversity for new device applications in the future. So this is why these materials are being studied quite intensively at the moment. So the observations of spin-Seebeck effect have really come around in the last 10 years or so. Spin-Seebeck and spin-Peltier of analogues of these classical physical phenomena. So what are these materials about and what do they look like? Well, actually what we have here is, in our particular case, these are ferrimagnetic materials. These are insulating materials, they're oxides. And if you place them in a thermal gradient, you can create a heat source or heat current inside the material. On top of the material is grown a heavy metal, usually platinum. So you have this interface between insulating magnetic state and a heavy metal. And what will happen is that the magnons become excited, and at the interface here, you will set up a spin current going inside the conduction electron. So the interaction between the magnons and the conduction electrons of the metal can give rise to this spin current. And that is basically described as a flow of angular momentum inside the metal. Now that spin current can then be transformed, because platinum is a large spin orbit coupling material. You can transform that spin current into a charge current. And that is then measured as a measurable electricity, transforming the heat into usable electricity. It's a thermoelectric effect. So if we look into our material systems, these are grown there in form of thin films. These are thin epitaxial films. So that means they're fully crystalline materials. And in fact, they're very highly crystalline materials. These samples are very, very highly crystalline, very beautiful, high quality samples. They're grown by methods like pulse laser deposition onto a substrate. So our substrate is this gadolinium gallium garnet, which is a paramagnetic material. And on top of that, we grow these thin films of iron garnets systems. So there's a gadolinium iron garnet, GD3Fe5O12, at about 20 nanometers thickness. And on top of that, we grow the platinum that I've described as part of the spin-Seebeck effect composite. But these materials are epitaxial. They will have epitaxial strain. So there's a strain which is given between the mismatch of lattices in the substrate, and that can be important also in tuning properties inside these materials. Strain is known to go inside band structure and affect many functionalities, not least magnetism too, and magnetic domains. So this is an important aspect in our materials. What happens to the thin films afterwards is that they become etched by lithography methods. So what happens is they become etched by lithography methods into these kind of hole bar probes here. So this is the hole bar structure as shown here. So the area away from the film here is completely etched away. There's only substrate, and all that is left are these hole bars. This is the part of the sample, and these are crystalline, purely crystalline. So I show a micrograph of the sample over here. These are the pads which are used to connect electrodes to measure the currents generated and apply the currents to the materials. And these have typical sizes. They're about 100 microns for the pads, and they come down to these wires, which are sort of the other micron size. In fact, with these lithography methods now, you can grow wires from about 2 microns all the way down to 200 nanometers by using different kinds of lithography methods. So all of these materials are very high quality indeed and state of the art, and that's what we come in with our X-rays to study. If I talk a little bit about the magnetic properties of these iron garnet systems, these are ferrimagnetic systems, which means that they have an antiferromagnetically coupled spins, but there's actually a net magnetic moment. The spins don't cancel each other out completely, and there is a net magnetic moment. So first of all, there are the iron sites. There are 2 ions in the gadolinium iron garnets. One is in an octahedral site, as shown here. And that is coupled antiferromagnetically with a tetrahedral site. So this is surrounded by oxygens in a tetrahedral. That gives a net iron moment, which couples antiferromagnetically with the gadolinium or the rare earth. And at very high temperatures over here, it's the iron that kind of orders and it's dominating. So the iron below the nail temperature is the strongest magnetization. The gadolinium is actually very weak, but as you cool down, I'm showing the temperature dependence here, what happens is the magnetic moment of the gadolinium or the rare earth grows as the temperature goes down, and eventually it reaches a point which is called the compensation temperature around 250 Kelvin, where these magnetic moments actually cancel. So there's no longer any magnetization measurable at all. It goes down to zero. That's because all the magnetization is equal and opposite. As you continue to cool the system, the gadolinium eventually takes over. It dominates the magnetization. So that will then align with a magnetic field if it's applied. It's the gadolinium moments that basically dominate at lower temperatures. So if we look inside these materials, if we look inside when we measure the spin-Seebeck effect in these materials, there are two sort of strange effects that really come on. And this is the first part of this that I want to address is if you apply the magnetic field, and this is the spin-Seebeck voltage that you measure as a function of applied magnetic field, you can see that it's actually very noisy at zero field. It's got this kind of hysteresis effect, and it seems that there's some kind of quenching, or if you like, of the spin-Seebeck voltage as you go to 0 volts, and that kind of suggests that there are maybe some domains inside the structure. It looks very much like a hysteresis. It's suggesting that there's some kind of domains that is actually acting in a way as not making the efficiency very strong inside these materials. So this is what we wanted to address. We wanted to see if there was some kind of magnetic texture inside the materials that was actually inhibiting the efficiency of thermoelectric generation. And in these materials, the magnetic moments are oriented along the 1-1-1 direction, and they are 1-1-1 direction of a cube. There are basically 4 equivalent 1-1-1 directions of a cube, which can give rise to essentially 8 in principle magnetic domains. So you can have a lot of magnetic domains in these structures. The second part of this talk is going to talk about another effect that is kind of interesting. First of all, if you look at the voltage or the current that's generated by spin-Seebeck effect as a function of temperature, there's a sort of sign change here at higher temperature, and that's kind of maybe easy to understand due to the fact of these switchover of the sublattices, the iron and gadolinium sublattices at T compensation. Won't be quite well understood, but there's another sign change at lower temperature, which doesn't seem to be related at all to the magnetization. So the question is why? What is the origin of that effect? And because the spin-Seebeck effect is believed to be due to the magnon properties, what we wanted to do is characterize the magnon properties and see what if we can get my own information on this second sign change. So that's really the second part of this talk. So first of all, let me talk about magnetic scattering. Before I talk about magnetic scattering, I'll talk about normal charge or atomic scattering of X-rays. And that is, as we all know, is basically related simply to the number of electrons. So your charge scattering length, FC, is normally related to the number of electrons times by R0. And so the more electrons you have, the stronger the scattering you have. So, hydrogen is a very weak X-ray scatterer. Iron is a very strong X-ray scatterer, and gadolinium, which has lots more, 60 electrons, is even more stronger scattering. So that's kind of a simple principle. But if we look at the cross-section, if we look at the cross-section for magnetic scattering, so here I show what is the interaction of an X-ray with magnetism. It actually is a very different function, essentially. So what I'm plotting here is the energy. So here I have 1 k electron volt in the soft X regime, 10 kilo electron volts in the hard X-ray regime. And this is the cross-section, the magnetic cross-section. I've plotted it in R0 squared. So it's something similar to intensities. If you actually look at the cross-sections here, what you can see is that there's a sort of solid line background here. This is what's called a non-resonant scattering term, which is really going as the square of energy. And then you come to these sort of absorption edges where you can just tune into these absorption edges and you get this great enhancement of magnetic scattering. And that is the effect that we really want to tune into. So this is where we can boost our magnetism and start to use and study magnetism in a way to study very thin magnetic structures that I've just shown, or even looking at magnons. So in the talk here, I showed this is the scattering, the non-resonant scattering is even very much weaker than the scattering from a small hydrogen atom. So, you can see these quite easily with high flux third generation synchrotron sources. So these are Bragg peaks, non-resonant magnetic scattering peaks, which you can resolve very easily these days, even looking at these very low levels. what we've done in this work is the first part is this resonant nano diffraction, and we've been working in the hard X-ray regime at these resonances at the gadolinium L edges. And the reason we've been doing that is because we need to do this diffraction. So this has been key to our work, is doing diffraction. These gadolinium iron garnets don't give any Bragg reflections at all in the soft X-ray regime. So if we were working at the iron edge or the gadolinium M edges, we wouldn't see any Bragg peaks at all. We wouldn't be able to do diffraction. So this was not available to us for this particular type of system. We have to work in the hard X-ray regime and at these energies. However, for the resonant inelastic scattering, the RIXS data, which I'll show later on, we've been working in the soft X-rays and being able to tune into this very nice, strong resonance of the iron L edges. So an important aspect of this work has been being able to change the polarization and work with circular polarization. So I'm going to go into why that is right now. If I look at the intensity, this is the diffraction intensity. So I'm showing here the structure factors for diffraction peaks. That's the e to the I cubed r structure factors, which is quite well known. What is the intensities that we would expect for circular polarized light? So the basic can basically break down into three terms. The first term here is this charge scattering term. This is the atomic scattering, and it's simply related to the FC term, the number of electrons that I showed before. There's also a polarization term prefactored. The second term is pure magnetic scattering, and that is related to the strength of this FM term, or it's usually dominated at an absorption edge by this resonant scattering response, those peaks that I showed in the previous slide. There's also a prefactor term, which is dependent on the magnetization direction, the moment direction, and Ki and Kf are simply the incident and scattered wave vectors. So we'll go into a little bit more about those later, but there's a final term that this is the one that we've actually been using. This is called a charge magnetic interference term. So this is the one that was important in our measurement of this nanodiffraction. We've been exploiting this term, which is actually gives a strength, which is rated not just to the FM term, not just the magnetic one, it's the FM term multiplied by the FC term. So it's actually stronger than the pure magnetic term. Not only that, it depends on the helicity of the light. So if I come in with left or right light, this polarization helicity term will either be positive or negative. So this term here can be isolated in circular light just by taking the difference between left and right. And in fact, the charge scattering terms, or these scattering terms, can be isolated if I just take the sum. So by using circular light on these, looking at Bragg peaks, and this is kind of important to express now, is that the Bragg peaks that we are looking at in these ferromagnetic systems consist of both magnetic and charge scattering. So they both contribute to the same Bragg peak. The idea is we want to actually separate out the magnetic scattering from the charge scattering. And the way in which we do that is using this interference scattering, which is related to that scattering strength, not just the pure magnetic one. There's a similar effect, actually. If you come in with linear pi light, you can get a similar effect. So if I write out the intensity that's expected for pi polarized light, we have a first term, which is pure charge scattering, a second term, which is pure magnetic scattering, and the third term is the charge interference term. So this is again related to the strength of the number of electrons, total number of electrons multiplied by the strength related to the resonance that you were looking at. And it also has a polarization factor that depends on the direction of the magnetic moment. So this is where you can get magnetic information as well from this resonant term. Both of these terms give you magnetic information. Now, the pi light is one that is got an electric polarization in the scattering plane. Sigma light, which is the one that usually comes out of a synchrotron, this doesn't possess a resonant and interference term, so you can't really use the sigma light to do this trick of getting charge and magnetic information. So let's look again in a little bit more detail about these interference terms. So I'm comparing them here. And if I look again at these prefactors, depending on the magnetization measurements, you can see that these kf.m and the ki.m, these refer to terms really inside the scattering plane. So it's you are sensitive to magnetization in the scattering plane that you are measuring your diffraction in. If you look at the other one, the pi light, you are dependent on magnetization out of the scattering plane. It's the cross product. So that is the direction. This one here, this cross product, gives you magnetization this way. So they give you the same information on the interference term, but they are sensitive to different moment directions of the magnetization. And that's a nice part of this work, that we can actually get contrast, different contrasts to different domains just by changing the polarization. Other things to say about this is that this work, we're working in Bragg, we're always working in Bragg condition here. So we're talking about diffraction peaks. If going from 004 to 008, you will change the Bragg angle. And that in principle as well will change your contrast to domains. So the different domains will have different contrast just because you've got these different factors. If this was a magnetic moment direction, the projection onto these moment directions is different for the different Bragg angles. The second thing to say is that if you have a small angle scattering regime, so this is sometimes taken in a small angle scattering regime, you can do kind of imaging. This term here, this cross product term, basically depends on the sinus of 2 theta, the Bragg angle, and that gets very small, essentially negligible as you go towards a small angle scattering. So this kind of effect of seeing the moments out of plane can only really work in Bragg geometry where you have high angles. So what have we done? If we go back to our sample now, and what we've been trying to do, we align our sample in a particular way inside the inside our X-ray beam. So we align it parallel to the X-ray beam, the 110 direction, parallel to the X-ray beam, so that we can see that we'll have one of these type of domains aligned parallel to the beam, the other one anti-parallel, and the ones perpendicular to the beam. So as what I was saying before, is what we would anticipate is a very high contrast for these domains using circular light, and a higher contrast for these kind of domains using the pi light. And we can study the same Bragg peak and essentially get this kind of information. We access this information, the magnetic information, by using what's called a flipping ratio. So we have a circular flipping ratio, which is the difference between left and right divided by the sum. That can give us some magnetic contrast for the moments in the magnetization in the scattering plane. We devised another one which can be used to actually access the one for pi, and that's this flipping ratio. And that will give us magnetization responses to the ones perpendicular to that direction. And if we just simply take the sum, this is what I said before, the sum is basically, we're just left with the atomic structure. So in principle, using the same data sets of left, right, and pi, we can get information of magnetism in the scattering plane, perpendicular to the scattering plane, and correlate that with the structural one underneath, which is the atomic scattering factor, the normal one, by the sum. Our setup that we used on ID1, combining here Nanobeam to the X-ray Nanobeam and resonant X-ray scattering. This is what the setup was like. We had a phase plate. In fact, we borrowed the phase plate from the Xmas beamline, brought it to ID1. We worked at the gadolinium edge, as I said before. We could cool the sample down to 15 Kelvin. And then we started to use strongly focusing optics. So we can get down to, using this zone plate, we get down to a beam spot of about 200 by 400 nanometers, cooling down the sample and translating it in the beam and measuring the response on a 2D detector. This is the response of the phase plate giving circular polarized light. So using different angles of the phase plate, we can either get left polarized, circular polarized, or some pi polarized light incident onto our sample. It's interesting to note actually that in passing now that these experiments were taken at the old ESRF before the upgrade. So now if we go back to ID1, they're talking about the beam, the same sample spot using the similar optics. What they can achieve now with this very high emittance is now something like 30 nanometer beam spot. So you gain an order of magnitude in the beam size just from this new source as well, before even talking about the increase in coherent flux. That is also a very great parameter, because our resolution in the scanning diffraction is related to the beam size. So we already, if we go back to ID1, and we do have experiments to go back on ID1, just by using this smaller beam size, we should already increase our resolution. So here I come into some of the results. I'm showing here that these are the micrographs of our samples. This here is the starting diffraction data. So this is the intensity of a Bragg peak. So I'm looking at the sum of left and right. This is literally the scattering without any looking into magnetic objects for the moment. The blue areas are zero because there's no film there anymore. This is just a substrate, and we're looking at the film Bragg peak, not the substrate Bragg peak. And then we look at the scanning around on the beam. We can just map out basically these structures here very cleanly using this very small nanobeam of our device structures. Now, the bottom figure here shows the difference. This is the flipping ratio that I showed before, the circular flipping ratio. And we start to see some interesting contrast develop. We see these positively polarized or positively intensities, or in the flipping ratio in red, negative ones in blue, and basically 0 around here, which is green. And we can start to zoom into this. So this is like the 100 micron size, looking at those big pads, just scanning around and mapping out where these contrasts come. This is now a 15 nanometer zoom. So we zoom in again into these regions. I'm zooming down to 15 nanometers, and then we can go all the way down to 5 micrometer length scales here, zooming in. And it looks like there's a very large distribution in domain sizes, actually going all the way down even to the sub-micron stage size in these materials. So that's actually quite interesting. We couldn't resolve them anymore by going much further than our resolution, but our beam size. But they exist on a very long length scales in these materials. So that's the first kind of result we get. Now, what we wanted to test was whether these contrasts that we're looking at are really associated to the resonant scattering and magnetic domains or not. So one way to test this is to test it with theoretical calculations. So we have some theoretical calculations from Yves Joly at Institut Néel using his developed FDMNS code. And he can use this predicted circular polarized flipping ratio. And these are calculations of what we would expect for a domain which is aligned parallel to the beam in the beam direction. This is one anti-parallel to the beam direction, but in the scattering plane. And these are the ones which are perpendicular with circular light, which have only a very small component, which is the sort of the vertical component sticking out of the film. Is much smaller than the ones in the scattering plane like this. And that's what the theoretical calculations give. So what we have done here is done some more scanning diffraction at different energies. So we go away from the absorption edge down here, and essentially we can't see any contrast at all. And then we start to get the contrast and move in towards the, we're moving in towards the absorption edge. And you can see here that the first thing that happens, you start to see something arise, but it's actually a negative contrast, not a positive one down here. And that kind of agrees with the theoretical prediction that first of all, it will go negative. And then eventually, as you start to increase the energy, it will then go positive and then go away again, as you see down here. So going up. So this agrees perfectly with the theoretical calculations and gives us very strong evidence that what we are asking at is in fact magnetic domains from these material systems. So from that, we can also make a predicted contrast. And that's what we've shown here. This is the measured contrast by measuring these different regions as a function of energy. And that also agrees very well with our prediction from FDMNS. The second aspect of this thing that I referred to in the beginning is looking at the difference between pi and linear polarization. This is incident into the beam. So this is again is the circular polarized light, where we can see these images of domains, magnetic domains, both high and low, red and blue. What we can also see is a large region here, which is basically 0. And one possibility could be that this area is related to domains which are out of the scattering plane and therefore only very weakly picked up in these contrast map here. So if we come in with the pi light, what we can see is actually we pick out a domain here in this large area region, which kind of agrees with that scenario that this domain region here would be ones out of the scattering plane. The second, or the third thing that I want to highlight is again looking at the, I'm showing here the magnetization data, the magnetic data, the magnetic domains, zooming in, different features. And I want to compare that with the crystallographic information that we can get. So we can get two types of crystallographic information. The first is the total intensity. So this is the sum of left and right. So this is just the atomic scattering. And you start to see some features here which go along these kind of directions. And that's going along the 100 direction. We can also look at the crystallographic tilt information. So this, it basically moves the Bragg spot onto our detector, and you can trace that back actually to some kind of tilting effects in the crystallinity of the material. So this is basically tilting in milligrees that you get out. And these also seem to show some effects going along the 100 direction. And that seems to be somehow subtly correlated also with the magnetization, these magnetic domains actually in the 100 direction. So what is the nice thing about this, and this is kind of like the unique thing really of what we've done here, is being able to correlate with the same data set, magnetic information and charge information or structural information together to see how they basically interact. And things like strain and defects may eventually affect the magnetic contrast or the magnetic texture. So this is one way in which you can actually compare the two using the same data set. So that's actually a very powerful probe of magnetism, and it's different, for example, than something like PEAM or other probes that you can get to probe magnetic materials. Now I turn to what we would like to do with the EBS, and we have some beam time coming up this year, to where we can basically build on these nice experiments looking at the magnetic domains. Going back to ID1, one aspect of this is trying to use magnetic ptychography. This is a coherent diffraction imaging method, and it's very powerful in Bragg geometry. And I can just point out some of the strong points about Bragg ptychography. First of all, it's very powerful to study crystalline materials because you study Bragg peaks. It's got a very high resolution, which goes beyond the beam size. So we're not limited to beam size anymore. We can go below the beam size in our spatial resolution. In principle, it can get 3D imaging. So all of these maps that I showed before, these were just kind of 2D images. In principle, we can get the 3D imaging by doing these rocking theta scans at a Bragg peak. You can image strain. That's something that you can do in Bragg as well, which is also great because then you can correlate strain to what that's doing to magnetism in principle if you could develop magnetic Bragg ptychography. It's fully quantitative, and essentially you have an unlimited field of view because you just have to scan your sample around. I mean, in practice, that might be more difficult because of time limitations or stability limitations, but in principle, that's an unlimited field of view which you can have. And given that you have these large spatial they exist on space-time. The magnetic domains exist over this long length scales, that it's actually nice to have these large scale of view that way you can zoom in or zoom out to different areas with, again, a high resolution. So the way in this ptychography works is basically by finding phase from an algorithm, and you do the same kind of scanning. You scan various areas, but you have very strong overlaps. So you have lots of redundant information. And then you can put that into a phase retrieval algorithm, a computer algorithm, and eventually solve the phase. And what you will end up back with is two parameters, solving phase and the electron densities, essentially. So we have actually started to do this experiments at Nanomax beamline, looking at the structure of these materials. So here we zoom into this structural area, and this shows basically this is a map. This is the total diffraction map. So I'm away from circular polarization for the moment. I'm just looking at the structural information that's given off from this material. And here we show actually the Bragg ptychography reconstructions from that area. And this has been done in collaboration with Peng Li and Virginie Chamar, who are experts in ptychography. And they're working with us on this project of trying to develop magnetic ptychography. And what you can see here, this is the amplitude that was retrieved from those reconstructions. And what I show here on the left is actually the phase. So the phase actually shows some interesting information as well, that in the center of this kind of wire, the phase is essentially 0, but there are some effects towards the edge of that. And this is still preliminary data, but one aspect of that is that it could be due to some kind of tilting. So as you've cut out those wires by this lithography, and because they're under compressive strain, this can then lead to some sort of tilting towards the edge. So this is information that we didn't know before we started ptychography at all, actually. So that's kind of already very promising results. But what I wanted to do really is talk a little bit about contrasting some different methodologies, really, that, imaging and coherent diffraction imaging has been around for a while, actually, and studying magnetic materials. And this is something that we've been doing recently at the Soleil synchrotron using sextan, looking at these formation of skyrmions, which occur on the magnetic field in these are amorphous gadolinium multilayers. So we use a technique called holography, which is essentially in a small angle scattering regime, and you interfere your scattering, your diffraction, coherent diffracted image with a reference hole. Some really nice work has been done already with Claire Donnelly. These are in the group at Paul Scherrer Institute, looking at both Sachs ptychography and nanotomography and getting information on magnetic materials. And this is also really, really beautiful work using coherent diffraction in some of those ways. But this, again, is small angle scattering. So what we're trying to do here to distinguish that is a way of looking at Bragg peaks. So these are looking at crystalline materials as opposed to sort of amorphous ones or whatever, which are of technical relevance or technology relevance. You can also get other features about these kind of things as well. As I mentioned, you can get to the strain and correlate strain, and strain can arise from the epitaxial crystalline structure or even magnetostriction. In principle, you might be able to extend this also to look at Bragg peaks, antiferromagnetic Bragg peaks and antiferromagnetic materials, which haven't really been possible with these methodologies either so well. So it can basically go beyond, a little bit beyond what has already been done. And in particular, there's this idea of using the different polarizations of light, the pi and circular polarized light. So I don't know, I just better have a time check here. How much time have I got left? About 5 minutes or so. So I just need to maybe fast forward a little bit. Now I'm going to the Magnon projects. I may need to go through this quite quickly because of time constraints, but basically I've been through really what I wanted to show in the paper. The magnons, what we measure here in Q-space, you measure these dispersions of magnons with inelastic scattering. And in particular, in these kind of materials, these ferromagnetic materials, you can have different modes. One is an optical mode and an acoustic mode at lower energies. So if you want to study these with RIXS, RIXS has an energy resolution of around about 20 to 25 MeV. So it's very difficult to study these low energy excitations, but you can study these higher energy ones and just about come out. What we've been studying these things with is the neutron scattering. The neutron scattering actually has beautiful energy resolution compared to X-rays. So that's there we use a strength in looking at bulk materials for these things. So this is again to remind you, coming back to what this sign change is at lower temperatures. Can we highlighting the magnetic effect? So there's actually a theoretical paper by Gerrit Bauer and Joe Barker, which comes in to describe what happens at lower temperatures in this material, these gadolinium iron garnet. And it should be this interplay between these magnon modes. The lower energy alpha mode, which is the acoustic mode, and the optical mode, will just because of the exchange between iron and gadolinium that increases at low temperature. This will be basically elevated in energy, and a gap opening up above this horizontal line is the thermal energy. And actually these modes actually should have opposite chirality, so opposite polarization. The magnons have a particular polarization. They process around either in one direction or the other. In a pure ferromagnet, you only have one possible direction, one possible mode, but in antiferromagnetics, you can have different modes that can be separated out because of these different exchanges between the sublattices. So the idea here is that these two modes pump differently. They do the spin pumping and generate a spin current in different ways. So the difference, the total spin current is given by the difference, and that will essentially switch over when you go to the compensation temperature. And because of the gadolinium and this effect here going away, that at lower temperature, it will actually it will give a sign change in the spin current generated. So we've used magnetic neutron scattering, inelastic neutron scattering, and I go very quickly here that there are two types in this inelastic, polarized inelastic neutron scattering methods of interest. One is that you have a spin up neutron that can be scattered with the same polarization spin up. So these are called the non-spin flip channels. So you have up, up, or down, down. This still gives you information on atomic excitations like phonons. The magnon excitations come from spin flip channels. So this is up being flipped down and down being spin up, being flipped up. And where you can get chirality information in neutron scattering is a difference. So if you have an asymmetry, essentially an asymmetry in the intensities of up and down, that will tell you about chirality. And that's really where we come into this, looking at these materials with inelastic neutron scattering. And what you see here, these are the magnon modes which are measured as a function of temperature. And you can see, first of all, there's a gap that opens up and it goes above the Fermi level. So not the Fermi level, the thermal energy, which is shown by the vertical line here. And what you can see is that there's a chirality. It's very clear because you have one channel is finite, the other channel is essentially zero. So that's telling you that these modes are essentially 100% chiral, so very strongly chiral. And you can see that at the temperature, the compensation temperature, they switch over. So the red becomes blue as you go through that compensation temperature. that's already agreeing with the theory of that was developed by Barker and Joe, Barker and so we can look also at the lower levels, and they seem to have a different chirality that basically dominates at lower temperatures. So this kind of agrees with the theoretical models that were given for this material. So we get a support for that from the inelastic neutrons, a very strong support for that. But what I really wanted to share was what we could do also with RIXS. So we've been doing RIXS experiments at I-21 at Diamond and at ID32 at the ESRF. And this is some recent data where we show the using circular polarized light. And in principle, circular polarized light can give you information on chirality as well. So the idea was that we would actually try to see if we could see some differences in the magnon chirality using these circular light probes here, albeit with a broader energy resolution. So you can see this is the first magnon mode below the compensation temperature, and this is the same mode above, and you can see this basically the switching that goes on above and below that temperature is very similar to what we've measured with neutrons. So it might be that this is a methodology of also probing the magnon chirality in these materials in a complementary way to what we've done with the neutrons. So I can show here actually some of the results we measured with the neutrons. The width of the elastic line here is essentially a measure of the energy resolution. You can see that the energy resolution is so much greater for the neutrons than the RIXS. However, you can see the sort of similar effects going out here, that you can see this kind of switching over the differences between left and right. It seems to reflect also the polarizations that were determined with neutrons. What is the advantage of this is that with the neutrons, of course, we have to use very big single crystals to do inelastic neutron scattering. With RIXS, we can apply this in principle to thin films, and even thin films with gadolinium inside. Gadolinium is a very strong neutron absorber, unless you use very expensive isotopes. And so we've been able to make a comparison really between what we've measured with in single crystals with thin films. So the conclusions really of the talk, first of all, there was this nano diffraction, which reveals a spin texture that seems to inhibit the thermoelectric efficiency. And we can develop a methodology to correlate magnetism and crystal structure with these data sets, also using this polarization contrast, which wouldn't be possible in forward scattering. We've got this potential use of EBS, but we hope that we can try to develop some kind of high resolution, spatial resolution, 3D magnetic ptychography, correlating again magnetic structure and strain effects also in 3D. We used the polarization, polarized neutron elastic scattering to get a lot of information on the magnon properties of these materials. And what we've done recently is try to complement that with thin films using circular polarized RIXS to get information possibly on the polarization of the magnons too. So the final slide that I wanted to share here is really a thank you to the many collaborators that we have working on all this with me, not least Walter Meinsner, who create these beautiful samples, Stefan Braggs, who works with me also on some of the experiments, the X-ray experiments and neutron experiments, and he grows these fantastic samples that we're very fortunate to work on. So that's the end of my talk, and we can leave everything over to some questions. Thank you for your attention.
Thank you very much, Danny, for the beautiful presentation. We don't have questions yet, but there was a message in the chat from Bill Sterling giving you greetings.
Oh, greetings to Bill. Thank you.
So, so I invite all participants to ask questions. Yeah, we have the first questions from Tim Simon. I had a question, actually two. At the compensation point, you expect the gadolinium moment to stay finite if you see going to zero just because of domains. Tim, could you reformulate your question because it's not so clear to me.
Well, The magnetization, I think it's easy to answer. I mean, it's going to zero because the magnetic moment, the size of the magnetic moment is cancelling. It's really nothing to do with domains. So I think you would measure that in magnetization with zero, with a field onto the sample. So
no, but the compensation point has nevertheless an important influence on domains, because there the cohesive field diverges, goes to infinity because the moment goes to zero. Macroscopic moment goes to zero.
Yeah.
But still, the magnetic scattering, the inelastic scattering by magnons should not disappear there.
Yes, well, that's true. And yeah. So if we go to the compensation temperature, we only have data above and below, not right at the temperature.
So yeah, Tim comments, yes, I understand, but the black curve was just the gadolinium moment, question mark.
In the magnetization data?
I guess so, yeah.
It might take me a while to go back, so I can just go back to this. Okay, so here we have, I think, field cooled and zero field cooled. Now this is the total, it's squid data, so this is basically measuring the magnetic response outside.
Oh, it's a macroscopic magnetization, not the gadolinium.
Yeah.
Okay.
Measured outside the sample.
Okay, some more questions.
Sorry to ask the question.
Okay. Tim Zeiman is coming into my office. So
you're at work. Hello, Tim.
So this is a question.
Well, I had a second question, was more general. Sorry, I better off my computer. Can you hear me?
Yeah.
No, the second question was just, I don't know what what about the hope of doing same sort of experiments on metals rather than insulators? Could you?
I think in principle it could work. I mean, here we need a very good crystalline material. So these materials are made by pulse laser deposition is one way, but in principle you could make thin films which are metallic, and if they're provided that they have a nice structure, we could do that. Yeah. So.
But I mean, for the inelastic, it's hard because of extra background for electron hole. But for the diffraction, you say you could do it.
Yes, depending on what the metal was. I mean, if it was, you had to work in a hard regime and work on something like an iron, I think that would be just very difficult because the magnetic scattering is very small in the hard X regime for iron, and if you had to do diffraction as well, so that wouldn't.
I was actually hoping iridium manganese.
Oh, iridium manganese. Yes, I think so. Yeah. Okay. I think at the iridium edge, possibly you could see something. Yeah.
Okay, sorry.
Okay.
Crystalline.
Thanks. I have another question. So there are 8 easy axis directions for the magnetization along the 8 111 directions.
Yes. Well, yeah.
Can you saturate the sample and having it in a single domain state?
Yes. Yeah. So in fact, the neutron measurements that I showed, and actually the RIXS data, they're all taken in applied field. So for the neutron data, we have a magnet, an electromagnet inside. It's inside a cryomagnet. For the RIXS measurements, we used a permanent magnet. So the samples are mounted onto a permanent magnet, and that's enough to saturate the moments along the 111 direction. It's very soft, the 111 direction.
Yes. So there is a question from Guillaume Berthier who says, "Hi Dan, very nice talk." And then question: can you distinguish between 111 and -1, -1, -1 domains, so opposite directions?
Yes. 111 and -111 is the strongest contrast, I think, that you would have. But whether you can, how can I explain this? How do you can't distinguish between, I think you can't distinguish between this, if you see what I mean. You don't know whether, how can I say that?
That's because you have the interference between magnetic and non-magnetic scattering. So it's a linear method.
Yeah, let's go back to what the domains look like. Okay, so if we have this one sticking up like this along the 1, 1, 1, and then we have this 1, 1, 1 bar, so it's sticking along the difference is basically the orientation in the along the film direction, right? You see what I mean? It's a mirror image there, but it's the same direction along the beam, but it's flipped up and down in the z-axis, you could say. You can't tell the difference between those two domains
because you project on the cross product of wave vectors. You have a projection, right?
Yes, you have a projection, yes.
On which axis? On the cross product?
Well, for pi light, is he talking the cross product of?
If you look at the formula with the magnetic scattering in the intensity with the interference term.
No. I mean, the simple answer is we cannot tell the difference between all domains at all.
Not all, sure, but sure. Some of them.
Some of them, yeah.
If you go back to the slide where you have the yeah, it was, I think it was that one. The next one.
Yeah. This one, right?
Interference. Oh no, it's not a cross product because you project on the average of on K plus Ki plus Kf.
This one here, yeah.
Yeah. Well, plus the cosine theta. So it's in linear polarization, you project on the cross product. Yeah.
Yes, in linear polarization is the one out of the scattering plane.
Otherwise, it's a more complicated expression.
You can't tell a difference between when you do the cross product, the one that's sticking out of the scattering plane in one direction and out of the scattering plane in the other direction, like this. If my nose is actually the beam direction, then you can't tell the difference. You know.
Okay, if I see the formula on the upper half of the slide, you project M on a linear combination of Ki and Kf.
Yes, along with a projection term. Yeah.
So depending on how you are with respect to that, you can see or not see the contrast.
Yes. So I believe that what we haven't done in those experiments was really explore more Bragg peaks and going around different Bragg peaks, and then you can in principle predict what your contrast should be, because especially with this FDMS code, we know pretty much what it should be. And by going to different Bragg peaks, you could get that. We just didn't get time to do it in the original experiment.
Okay, so
you can get more information about which domains you are looking at by doing this at different Bragg reflections.
Yeah. So Guillaume Bettier says, I was talking about circular light, but that's what you are just showing here on the slide, I think, on the top part of this. Yeah. That should answer the question, I hope. Any more questions? Okay, so then I just have to thank Dan again for this very beautiful presentation. And I wish everyone a nice weekend and see you soon on the ESRF webinar. Thank you very much, Danny.
Okay.